Let's see, where were we? We had defined homotopy equivalence. We had started talking about contractible spaces, and most importantly, we'd seen the carrier theorem, rather the carrier lemma, which says that if you have a map, if you have two maps carried by the same carrier, which assigns contractible subsets to every simplex, then those two maps must be homotopic. Now we're going to use the carrier theorem to show, to prove two results that are extremely important for this course. And we're going to do them one at a time. And the idea here is that you can use carriers to get what's called a fiber theorem. Let me try and define what is going on here. And most of this will all take place in the simplicial world. So let F from K to L be a simplicial map. And now let's see what we mean by a fiber. So here's the definition. The fiber of this map F under a simplex tau of L is defined to be, so I'm going to write it like this. So tau will live on top of F. So F is under tau. And this is going to be the set of all simplices in K, not in L, all the simplices in K for which F of sigma is a face of tau. So this is the collection of all simplices in K whose F images end up being faces of tau. And that's the fiber of F under tau. And there are a few sort of elementary things to check about fibers. So check that for all tau in L, the fiber tau over F is a subcomplex of K. So it's not just an arbitrary collection of simplices. It turns out that if you have a face of a simplex in tau over F, then it ends up in tau over F. And the second thing to check is that whenever you have tau a face of tau prime in L, the fiber tau over F is a subcomplex of tau prime over F. So these behave like carriers in the sense that the complex assigned to a small simplex is going to be included in the complex assigned to a larger simplex. Okay, so these are designed to be sort of very compatible with our notion of a carrier. Okay, so with this definition out of the way, we can get straight through to the main result. This is a very, very deep and beautiful and important theorem in algebraic topology. This is called Quillen's theorem A. I'm going to write it here as Quillen's fiber theorem. And what we're seeing here is a baby version. That's just for simplicial complexes. There are versions of this type of result everywhere. And so if you want to Google for something, it should be Quillen's theorem A. Anyhow, so here's what the theorem says. If F from K to L is a simplicial map, so that for every simplex tau in L, the fiber tau over F is contractible, then F induces a homotopy equivalence between K and L. Now, I don't think we've used this exact language of inducing a homotopy equivalence between K and L before. So just to explain what that means, this means that there exists a G from the realization of L back to the realization of K, so that the induced continuous map of F composed with G is homotopic to the identity on either K or L, and I will never figure out which. So let's see. G, okay, so this is on L, and similarly, the other way to compose things, G composed with F, is going to be homotopic to the identity on K. That's what this means for F to induce a homotopy equivalence. That means there's some G that acts as a homotopic inverse to F. So the composites are homotopic to the identity the way you'd want. Okay, so in particular, if you have a simplicial map from K to L whose fibers are all contractible over under every possible simplex of L, then that guarantees that K and L are homotopy equivalent. Remember, we were trying to produce tools that will help us recognize when two simplicial complexes are homotopy equivalent, and this is a fantastic one. What's really, really fantastic about it is that you don't have to know anything about G. It's not, you just need a map in one direction from K to L with contractible fibers, and then the proof guarantees that a G exists without necessarily giving you a recipe for one. So you only need a map in one direction is the really big advantage of this theorem. Okay, let's see how to prove it. There will be 3 appeals to the carrier lemma in order to prove this theorem. So let's go. So first of all, let C be a carrier, or I guess I should say, since I'm going to give you an explicit definition, be the carrier for K in L. Is that the way we want it? No, that's not the way we want it. We want a carrier for L in the realization of K, given by. So we have to assign subspaces of the geometric realization of K to simplices in L. So C of tau is going to be the geometric realization of the subcomplex tau over F, which is the fiber. Now, the thing to check is that that this behaves the way we want, like a carrier. So if tau is a face of tau prime, then the realization of tau over F should include into the realization of tau of F prime, but that's one of the 2 properties that I wrote up in gray. So it's true, and you can check it from the definition. Good. So by the carrier lemma, there exists some continuous map G from L to K carried by C. And the claim I want to make is that this is the G. This G will be a homotopic inverse to the continuous map F from K to L. Okay, so the thing is that there's no uniqueness guaranteed by the carrier lemma. So what I mean is that there might be several such G's going from the realization of L to the realization of K. You can pick any one you like. The carrier lemma says that at least one exists, and if you have any 2, they're homotopic to each other. So I don't care which one, you don't care which one. The claim is just that this exists and that this G will work. Okay, so what do we need to check? We need to check 2 things. One, that F composed G is homotopic to the identity on L. So again, my favorite tool, everyone's favorite tool for showing that 2 maps are homotopic is to build a carrier. So consider the carrier, and this will be on L, so I'll call it C sub L. So this is for the simplicial complex L in the topological space, the realization of L, given by C of tau equals the realization of tau. So it's sending each simplex to its own geometric realization. If you had a face of this simplex and the realizations would sit inside each other, so great. And we know that every solid simplex is contractible. So this carrier certainly satisfies the requirements of the carrier lemma. And the claim is this carries both the identity 1L which is obvious because it's sending tau to its own realization. So it, of course, carries the identity map. And F compose G. And the reason it carries F compose G is because if you take G of tau, this must live inside tau over F by our requirement on G being carried by C, C being the carrier upstairs, which means if you apply F to this, it will end up being a face of tau and therefore a subset of the geometric realization of tau. So this is the reason. And F takes tau of F to the realization of not sigma, but tau for every tau in L. Okay, good. And to see the other direction, which is that G composed with the realization of F is homotopic to 1K, you again consider the carrier CK this time because it's for the simplicial complex K in its own geometric realization given by C of sigma. So you have to take a simplex sigma of K equal to, you assign to it the fiber over the image of sigma over F. So this. So you have to check that this contains, this carries both the identity and G composed with F. And more importantly, C sigma is contractible for every sigma by our assumption that F has contractible fibers. So that's it. Both directions are true. You have F composed with G, homotopic to the identity on L, and G composed with F, homotopic to the identity on K. And so that's it. The theorem is done. F and G constitute inverses of each other up to homotopy, and therefore K and L are equivalent. Okay. Now, this was, I mentioned at the beginning, this is a baby version of Quillen's theorem A. There are several generalizations or several flavors of this result. And let me tell you one that we will use. I'm not going to prove it because it's much more technical than this nice simplicial version. So it's this. If F from X to Y is a nice, meaning the technical term is proper, and surjective. Surjective just means that it hits every point in Y, and proper means that the inverse images of compact subsets of Y are compact subsets of X. Continuous map between nice, and here by nice I mean X and Y are locally contractible and Hausdorff, which are again point set topological conditions that are satisfied by everything we have seen. So every simplicial map satisfies proper and surjective. Every realization of a simplicial complex is locally contractible and Hausdorff. So these are just technical conditions that we haven't defined. And if you want to look them up, then there's a point set topology book somewhere in your future. So between nice spaces. Then if F inverse Y is contractible for all points Y and Y, then F induces a homotopy equivalence between X and Y. So again, the argument is similar to what we've done. You have to find a carrier, you have to block Y off into chunks that are contractible and build a carrier for each of those chunks. Okay, so these are sort of general versions of Quillen's fiber theorem. This one actually predates, I think, much of that work. This is due to Smale from 1957. If you want a precise reference, you should look up the accompanying lecture notes. Okay, so here's where we're going. So we now have a fiber theorem, and like I said at the beginning, the advantage of a fiber theorem is that you just need a map in one direction, and it sort of does all the work for you of showing that this map will form one half of a homotopy without ever building the second half explicitly, which is great. We're going to need it in a minute. And now our final important main theorem for this week is called the nerve theorem. And this is what gives our entire method of approximating point clouds with simplicial complexes or filtered simplicial complexes like the Čech and the Vietoris-Rips filtrations. That's what gives it all its strength. So here's a quick setup on the nerve theorems. This is the end of all the fiber stuff. So now we should talk about nerves. So setup. X is a topological space. We call a collection U alpha subset of X. Alpha is in some index set A, finite open cover. Finite open cover U if A, the indexing set is finite, of course. If each U alpha is an open subset of X. And most importantly, if X is the union of alpha in A of U alpha. So this is just a way of taking some complicated space X and breaking it up into pieces, into open pieces that are allowed to overlap. So here is one piece, maybe, for this X. So it has to be a subset, so I'm trying not to color outside. Here is another piece. Maybe it goes halfway up the hole, and here's a third piece. So here, of this decomposition of X, you might have something like this is U1, this is U2, this is U3, and if you take the union of all three of them, you get all of X. That's a pictorial example. Okay, so here's the basic idea. The idea is that you can build a simplicial complex out of any topological space X, provided someone gives you a finite open cover, just by looking at intersections of the covering sets. So let U alpha in A be an open cover of a topological space X. The nerve of U, this cover U alpha, is the simplicial complex. We'll write it as N of U with a bullet, where bullet means you're just allowed to range over all the things in A, all the alpha in A, whose D simplices are all subsets. I guess we should say K simplices because I'm trying to be consistent, are all subsets sigma of A, so of the indexing set, which indexes all the open sets in the cover, for which the following intersection, which I'll call the support of sigma, it is the intersection of all alpha lying in sigma, so that's not all of A, but some subset of A, U sub alpha, the intersection, is not empty with, and this is the important part, the cardinality of sigma, so that with dimension of sigma being k plus 1. So the support, so its k simplices are k generated by k plus 1 elements in the cover, so u alpha 1, u alpha 2, all the way up to u alpha k plus 1, so all of which intersect mutually. So it's not just pairwise intersection, all of them have to intersect. So maybe maybe I can show you what it looks like for this example. So we have U1, U2, U3. So U1 is a non-empty open set. So I guess I should say all of these are non-empty. It's part of the definition. So this U1 becomes a vertex. You see, a vertex is zero-dimensional. The set U1 is non-empty. So the support of that simplex is U1 itself. U2 similarly is its own simplex, zero simplex, and U3. And now whenever two of these intersect, you get to draw an edge. So because U1 and U2 intersect over here in the middle, you get to draw that edge between U1 and U2. U2 and U3 intersect in some non-trivial set over there, so you get to draw an edge. That's the nerve. It's a simplicial complex. And it's a simplicial complex no matter what X was upstairs. X upstairs is definitely not simplicial looking. It's just a topological space. But because of the finiteness of the cover, you get to build a simplicial complex. Now, the way I've drawn it, it should be very clear that, so this is N of U, that the realization of N of U and X may have very little to do with each other. In fact, in the worst case, you could just make the entire cover be X. U1 equals X, and then everything else you don't need. And then the nerve will always just be a single vertex. There's nothing to intersect. Everything is just one vertex. And so every topological space X with that bad choice of cover would give you just the nerve being a single vertex, which is not good. I mean, it's not telling you anything about the space itself. So here's the surprising fact, is the following. So this is the nerve theorem. So if you let U be a finite open cover of X, if for each simplex in the nerve of U, the corresponding support we know it has to be non-empty. But if it is also contractible, which is our key secret weapon, then the realization of the nerve is homotopy equivalent to X. Okay, so this is an amazingly cool result. Before we look at a proof, the most important thing about it is that it gives you a way, if you are interested in homotopy equivalence, which we are, it gives you a way of taking any topological space and finding a simplicial complex that's homotopy equivalent to it. The price you pay is that with your topological space, you must always be able to find an open cover so that all elements of the cover, all pairwise intersections that are non-empty, all triple-wise intersections, all four-way intersections, all of these are contractible. So you see how absolutely crucial the notion of contractibility is in all our homotopic goals. Okay, with that out of the way, let's see a proof. This proof is rated extremely clever. It's not obvious. So if you don't, I mean, no one watching or reading this for the first time should feel bad about not being able to come up with this proof on their own. It's slick. So here's how it goes. Let XU be the subset of the product of the two things that we want to say are homotopy equivalent. So you take a product of them given by, so it contains one thing from X, one thing from the realization of the nerve. So I'll write it like this. So ordered pairs, so little x in X, little u in the nerve, such that there exists some simplex in the nerve with X lying in its support and U lying in its realization. Okay, because it's a subset of the product, we have projection maps. From X of U, there's one projection map to X, and there's another projection map to the realization of the nerve. I'm going to label these maps P and Q. And so if you have XU here, P of XU is going to be just X, and Q of XU is going to just be U. So these are exactly the projection maps you'd imagine for a subset of the product of two topological spaces. Okay, so the claim is that both of these have contractible fibers, and then we can use the sort of souped up version of the fiber theorem I described after Quillen's theorem. So the claim is that P has contractible fibers. And now we're using fibers, i.e. P inverse X, so fibers over points, for all X in X is contractible. Okay, so if you want to prove this claim, you look at what P inverse X has to be. So P inverse X is all things of the form X is fixed and U, so that U in lies inside the geometric realization of some sigma, so that X was in the support of sigma. Okay, now which simplices are allowed to contain X in their support? Well, there's lots of them. Anytime a covering element contains X, so if U1 contained X and U2 contained X, then their intersection would contain X. But there is a largest such simplex, largest in the sense of having the maximal dimension. So if you let sigma X in the nerve be the intersection, be the collection of all alpha in A, so that X lies in U alpha, then sigma X is the highest dimensional simplex. In the nerve containing X, which is to say every other simplex that shows up over there is going to be a face of our maximal sigma X. Therefore, P inverse X is just homeomorphic, homeo, to the geometric realization of this maximal sigma X. Now, sigma X is contractible because it is a solid simplex of some dimension. So we're done with the claim that P has contractible fibers. So it remains to show that the other map Q has contractible fibers as well. And if we do that, then we are done, because if you go back up to this diagram, the fact that P has contractible fibers has shown that X and this space XU are homotopy equivalent. And if we show that Q also has contractible fibers, then we'll be able to show that XU and N of U are homotopy equivalent. And so if you string all of that together, then X and N of U must be homotopy equivalent. And we'll have done this without ever building a map from X to N of U or N of U to X. This is the power of the fiber theorems. You don't have to build a direct map. You can just sandwich a space in the middle, build two maps with contractible fibers, and you get homotopy equivalence. Okay, so to see that Q has contractible fibers, we write again Q inverse of U. So choose some U in the geometric realization of the nerve. So Q inverse U is going to be all XU, so that X lies in the support of sigma, where sigma is a simplex in the nerve of U containing X in its geometric realization. Now again, if you go back to the definition of the geometric realization, there is a unique simplex sigma. Unique simplex sigma containing U in its interior. So all these, let's say sigma interior. So we'll call this sigma U. So the geometric realization of any simplicial complex was defined by taking an affine embedding of its vertices and so on, and then looking at a union of the affine embeddings of all the simplices. And now there's going to be a unique simplex so that this U lies in its interior. So that's what I'm calling sigma U. So Q inverse U is homeomorphic to the geometric realization of sigma U, which again, contractible. So putting all of this together, we get that X is homotopy equivalent to X of U, thanks to the map P having contractible fibers, which in turn is homotopy equivalent to the nerve of the cover U, thanks to the map Q having contractible fibers, and so we're done. And here is the main reason we are talking about this theorem at all. So as a consequence, or as an application, here's a nice corollary. If you let M subset of Rn be a finite set of points, then for every epsilon bigger than 0, the check filtration, which we saw near the end of week 1, and I believe we write a check subset epsilon M, is homotopy equivalent to the union of balls, of open epsilon balls, around the points of M. Okay, this is why we did all the hard work. All the carriers, all the fibers, all the nerves was for this theorem. This is saying that our method of building filtered simplicial complexes around these points is going to give, at least up to homotopy, an absolutely faithful approximation to the union of balls. And the proof of this little application is extremely simple. Note that M plus epsilon, by definition, is exactly M plus epsilon is the union of points in M and then balls of radius epsilon around those points. So B epsilon X, this just means ball of radius epsilon around the point X in Rn. But, or really I should say instead of but, it's not a surprise, it's so, the collection ball epsilon x as x belongs to M forms an open cover of M plus epsilon. And more importantly, all intersections are contractible. So I haven't proved this, but you can use the straight line homotopy trick to show that anytime you have a convex subset of Rn, it's contractible. That's one of the exercises of this chapter. And because balls are always convex, the intersections of balls are convex, and the intersections are contractible. So by the nerve theorem, M plus epsilon is homotopy equivalent to the geometric realization of the check complex around M at radius epsilon. So this is great. This is one of the reasons we defined the check complex, even though it was slightly more, the check filtration was slightly more intricate to define than the Vietoris-Rips one. And the warning is that there is no such result for the Vietoris-Rips filtration. So that one's easier to define, but it doesn't have the solid homotopic guarantee. We'll see more in the next lecture.